Have you ever looked at your GPS and wondered if that little blue dot is perfectly where you are? Or, if the map you're holding truly represents the ground under your feet with absolute, pinpoint precision?
Yeah, it's a good question. We often take it for granted.
Right. We all learned in school that the Earth is a sphere, or maybe, a slightly squashed sphere. But what if I told you that simple mental image, a great starting point, it barely scratches the surface of how we actually map and navigate our incredibly dynamic planet?
That's a really crucial point. Because while the concept of a sphere gives us a basic intuition, the reality of Earth's geometry is far more intricate.
Intricate how?
Well, it's a shape, subtly sculpted by its own rotation, its dynamic interior, and the ever-present pull of gravity. Understanding these nuances isn't just for specialists, it's actually vital for anyone interacting with spatial data, whether you realize it or not. So our exploration today will focus on two primary conceptual models that let us accurately describe and measure the Earth's shape: the mathematically smooth spheroid and the gravity-defying geoid.
Got it. So our mission today is basically to demystify these two crucial concepts, the spheroid and the geoid. We want to show you how they work together, why they're fundamentally different, and maybe most importantly, what happens when you don't use the right one.
Exactly. The consequences can be surprisingly significant.
Yeah. You'll discover how these invisible models influence everything from the precision of your GPS navigation right through to the foundational planning of massive civil engineering projects. We'll unpack why choosing the correct reference system, things like the historic Everest spheroid or the ubiquitous WGS-84, why that truly matters for tasks ranging from detailed local mapping to global satellite positioning. By the end of this deep dive, you'll have, hopefully, a much more nuanced appreciation for the complex geometry of our home planet. So let's cut right to it. The Earth is not a perfect sphere, not even close. Really.
Not even close.
Instead, it's what we call an oblate spheroid. Now, for those of you already nodding along, you probably know what I mean. But for others, imagine this. Take a perfectly round ball, then gently push down on its top and bottom, squash it slightly.
Yeah, just a little bit.
That slight flattening at the poles and the corresponding bulge around the equator, that's an oblate spheroid.
And that subtle deviation isn't just some, arbitrary geometric curiosity. It's a direct consequence of fundamental physical forces at play.
Okay. Like what?
Well, the primary culprit is the Earth's continuous rotation. As our planet spins on its axis, centrifugal force effectively pushes material outwards. This is most noticeable at the equator, where the rotational speed is highest.
Okay. Like swinging a bucket of water.
Exactly like that, yeah. Think about swinging a weight on a string. The faster you spin it, the more it wants to fly outwards. The Earth experiences a similar effect.
Gotcha.
And compounding this, the Earth isn't uniformly dense inside. It has what we call a heterogeneous mass distribution.
Meaning it's lumpy inside.
Kind of, yeah. There are variations in the density of its material within the mantle and core. These variations create irregularities in its gravitational field, which further contributes to its unique, slightly irregular shape, makes it deviate even more from that perfectly smooth mathematical ideal.
Okay, so if we zoom out a bit, why does this oblate spheroid shape matter beyond just being a cool fact?
Yeah.
Why can't we just stick with the perfect sphere model we learned about in, grade school?
Well, and every time you use GPS for navigation, whether you're driving a car, piloting an airplane, guiding a ship, you're relying on sophisticated calculations that have to account for the Earth's true complex shape. Remote sensing, too, using satellite imagery to gather critical information about our planet's surface, its health, environmental changes. It depends entirely on these models for accurate data positioning. And crucially, the global positioning system, GPS itself, simply wouldn't function with the incredible accuracy we now kind of take for granted without these precise definitions.
Wow.
Without them, our maps would be inaccurate, our GPS readings could be off by potentially significant margins, not just meters, but possibly hundreds of meters.
Hundreds, really?
Yes. And our global systems just couldn't communicate or function cohesively. So this brings us to a fundamental challenge. How do we even begin to define such a complex, dynamic shape in a way that is both accurate and usable for all these practical applications?
And this is exactly where our two main models come in. The spheroid, sometimes called an ellipsoid.
Right. Ellipsoid is probably the more technically correct geometric term, but spheroid is commonly used too.
Okay. The spheroid and the geoid. They both aim to describe Earth's shape, yes, but they serve very distinct purposes in spatial measurements. Understanding their differences isn't just for geodetic engineers. It's key to truly being, well-informed in geographic studies and for making sense of the digital maps and location services that are just seamlessly woven into our daily lives now.
Absolutely. They're the invisible foundation.
Okay, let's start with the spheroid or ellipsoid. This is the more mathematical of our two models, you could say.
Yeah, definitely the mathematical one.
And it's the one we often implicitly rely on when we talk about coordinates like latitude and longitude. At its heart, a spheroid is a mathematically defined, smooth surface.
Perfectly smooth.
You can visualize it by taking an ellipse, think of like an oval shape, and rotating it about its minor or shortest axis. The three-dimensional shape it traces out is a spheroid. Its purpose is to be a simplified yet incredibly powerful model of Earth. And it's chosen for very good reasons, right?
Absolutely. Its smooth, predictable geometric properties make it incredibly easy, or at least easier, to calculate positions, distances, and areas on its surface. It's computationally advantageous, which is a huge benefit compared to trying to do calculations on the Earth's actual messy physical surface.
Right, because the real Earth is bumpy.
Very bumpy, relatively speaking. Mountains, valleys, trenches. The spheroid smooths all that out into a nice, neat mathematical form.
Okay, so how do we define a specific spheroid? Like, what makes one different from another?
Good question. To truly leverage a spheroid for mapping and positioning, you need to grasp its key parameters.
Yeah.
These are just abstract numbers. They essentially encapsulate the specific geometric fingerprint of that particular spheroid, defining precisely how it models our planet.
Okay.
First, we have the semi-major axis, usually denoted as A. This is basically the equatorial radius, the distance from the center of the spheroid out to any point on its equator. Represents the longest radius.
Got it. Out to the bulge.
Exactly. Then there's the semi-minor axis, denoted B, which is the polar radius, the distance from the center up to either of the poles. That's the shortest radius.
Centered to the flattened top or bottom.
Precisely. And finally, and this is where the squashed part gets quantified, we have the flattening, or F. This is calculated as FF.
Okay, Matthew, but what does it tell us?
It tells you exactly how much the spheroid deviates from being a perfect sphere. A smaller F value means it's closer to a perfect sphere, while a larger F means it's more noticeably flattened at the poles. These three parameters, A, B, and F, are the fundamental building blocks. They're the blueprint, if you like, that define the entire geometry of a specific spheroid.
So it's like designing a slightly squashed ball. You need to specify its longest radius, its shortest radius, and exactly how squashed it is.
That's a great analogy, yeah. That's exactly it. Those parameters make it a powerful and efficient tool for mathematical modeling.
Now, here's where it gets really interesting. Because as you said, the Earth's gravity isn't perfectly uniform, and the land and oceans vary a lot. So does one single mathematical model fit everywhere perfectly?
Well, that's the tricky part. Achieving a perfect fit everywhere simultaneously with one simple mathematical shape is actually quite difficult, if not impossible.
Right.
So to address different needs, sometimes you need incredible accuracy just locally. Other times you need consistency across the whole globe. We've developed two main types of spheroids. Each serves a distinct purpose and is optimized for different applications.
Ah, okay. It's like having different kinds of maps, right? Like a detailed local street map versus a big world atlas.
That's a perfect comparison. Each is designed for its own specific job.
Okay, so let's talk about the first type. Imagine you're a surveyor, maybe working for a national mapping agency way back when, or even today, for certain specific tasks.
Yeah.
You need to create an incredibly accurate map, but just for your country or a specific region.
High precision locally.
Yeah, maybe you're charting new railway lines or defining property boundaries really precisely or planning some big regional development. You wouldn't necessarily want a global average model that might be slightly off in your specific area, right? You'd want a model that fits that precise local topography as perfectly as possible.
Exactly. And that's precisely what local spheroids are designed to do. Their primary purpose is to closely match the Earth's actual shape specifically, what we call the mean sea level, or the geoid, which we'll get to, but within a limited specific region or country. They are optimized for intense local accuracy.
So what makes them tick? What are their characteristics?
Well, these local spheroids have some very distinct characteristics that set them apart from the global ones. And understanding these is really key. First, as you said, they are tailored for regional accuracy. Their creators meticulously calculated their parameters, those A, B, and F values, to prioritize fitting a smaller area as precisely as possible, minimizing deviations within that zone. This often meant extensive, painstaking ground-based surveys over many, many years. Think triangulation towers across whole countries.
Wow. Okay.
Now, crucially, their centers are not necessarily aligned with the Earth's actual center of mass. This is a fundamental point.
Wait, the center of the model isn't the center of the Earth?
Not necessarily, no. They are deliberately offset from the true geocenter to achieve that absolute best regional fit. They prioritized local precision over perfect global alignment, which made sense with the tools they had.
What?
Interesting. And historically, they were often based on these classical ground surveys, using those painstakingly accurate terrestrial measurements to define their shape and position relative to the local landmass. This was the state of the art for centuries.
Right.
And because of these regional optimizations and those deliberate offsets, heights and coordinates derived using local spheroids are not globally consistent. This is a major takeaway. Data from one local spheroid system won't seamlessly integrate with data from another or from a global system like GPS without careful and often complex transformations.
So a map of India based on its local system won't line up perfectly with a map of, say, North America based on its own local system.
Not without adjustments, no. Or even with a modern satellite image, the coordinates would be different for the same physical point on Earth.
Okay, can you give us an example?
Absolutely. A fantastic, truly iconic example of a local spheroid is the Everest spheroid, developed way back in 1830.
Everest. Named after Sir George Everest, the guy Mount Everest is named after.
The very same. He spearheaded them. Yeah, the numbers themselves aren't crucial to memorize, but they precisely define its unique, regionally optimized shape. And the Everest spheroid has been used extensively by the Survey of India for topographic mapping for nearly 2 centuries. It became the absolute backbone for all their geospatial products for a very long time.
So the key takeaway here is that coordinates and elevations based on that Everest datum differ significantly from global systems like WGS-84, which our GPS uses today.
Exactly, sometimes by hundreds of meters. So if you're looking at an old Indian map or working with any historical survey data from that region, you're almost certainly on the Everest spheroid. And its numbers will not directly align with what your modern GPS device tells you without a proper transformation.
That's a really important practical point. Are there other examples like Everest?
Oh, yes. Other prominent examples of local spheroids include the Clark 1866. That was foundational for early mapping in North America, formed the basis for many early North American datums. Another significant one is the Bessel 1841 spheroid, which saw extensive use across Europe and also in Japan, defining the national grids for many countries there.
Okay.
They all share that characteristic. Regionally optimized, non-geocentric, and excellent for their specific limited areas, reflecting the pinnacle of geodetic science for their era.
Okay, now let's flip the coin. What if your needs go beyond just one country? What if you need to track something globally, or you're launching a satellite into orbit? Or your smartphone needs to pinpoint your location anywhere on the planet with, like, consistent accuracy.
Right, the game changes at the global scale.
Regional accuracy, while important for local stuff, isn't enough then. You need a global, unified standard that works everywhere. Enter global spheroid.
Exactly. Their primary purpose is fundamentally different. It's to provide a best fit ellipsoid for the entire Earth.
A global average, kind of.
Sort of, yeah. They sacrifice some of that minute local precision you get with a perfectly tailored local spheroid, but they do it in favor of overarching global consistency. They create a truly universal framework.
And what makes them tick? How are they different from the local ones?
Well, these global spheroids offer distinct and really invaluable advantages for worldwide applications. They're foundational to pretty much all the modern geospatial tech we use. Their most important characteristic is that they provide globally consistent coordinates. Meaning a latitude and longitude pair derived using a global spheroid in, say, London will be perfectly compatible and directly comparable with a coordinate pair derived using the same system in Sydney. It ensures a uniform reference frame across the entire globe.
Okay, that's huge for things like GPS.
Absolutely critical. And another key difference, these spheroids are geocentric.
Ah, so their center is the Earth's center of mass.
Yes. Their defined center coincides with the Earth's actual center of mass, or our best estimate of it. This is a fundamental difference from the often offset local spheroids, and this geocentric nature is absolutely vital for space-based applications because satellite orbits are calculated relative to the Earth's center of mass.
Makes sense. Any downsides?
Well, there's a slight caveat. While they provide that global consistency, they may not align perfectly with local geoids in every single spot, resulting in small vertical or horizontal discrepancies in regional measurements. They inherently sacrifice some tiny bit of local precision for that global consistency. But it's a trade-off that's entirely appropriate, even necessary for their intended global use.
And their applications are broad, right?
Incredibly broad. They are the bedrock for satellite navigation systems like GPS, that's the big one, obviously, but also GLONASS, Galileo, Beidou, all of them. Also, remote sensing platforms, global climate models that need a consistent Earth surface to work on, and international cartographic standards. Without these global spheroids, global communication, data sharing, international collaboration, it would just be a chaotic mess of incompatible coordinate systems.
Okay, so what's the main global spheroid we should know about?
The undisputed king of global spheroids, the one you've almost certainly used countless times without even realizing it, is WGS-84. That stands for the World Geodetic System 1984.
WGS-84. I think I've seen that in GPS settings sometimes.
You probably have. It was developed by the United States Department of Defense, initially for military purposes, but its utility and precision quickly led to its adoption as the universal standard for GPS and countless other civilian applications worldwide.
And its parameters are different from Everest's.
Yep. Subtly different, but enough to matter globally. It has a semi-major axis, A, of 6,378,137.0 meters, and a flattening F of 1 telage 98.257,223,563. Again, don't worry about the numbers, but notice they are different from the Everest values we mentioned. Even small variations lead to significant differences on the ground when you scale it up globally.
Right.
The universal adoption of WGS-84 for GPS, for Geographic Information Systems, GIS, for virtually all satellite positioning, is really a testament to its effectiveness as a global framework. And it's not static, it's continuously maintained and refined by the U.S. National Geospatial Intelligence Agency, ensuring its compatibility with modern geoid models like EGM-96 and EGM-2008. These are models of the gravity field we'll talk about, ensuring its continued relevance for decades to come.
Are there others besides WGS-84?
Yes. Another significant global spheroid is GRS-80, the Geodetic Reference System 1980. It's very similar to WGS-84 in shape and size, and it's notably used as the basis for NAD-83, the North American Datum of 1983, which is widely used in the U.S., Canada, and Mexico. There was also the International 1924 system, an older but historically important global system used before satellite geodesy really took off.
Okay.
But they all share that fundamental characteristic, geocentric, aiming for global consistency, providing that unified framework for measurements across continents and oceans. So this really brings up an important question. Why have both? Why didn't we just ditch all the local ones once we had powerful global systems like WGS-84?
Yeah, why keep the old ones around?
Well, the comparative summary in our source materials really lays out the key distinctions and highlights why both local and global spheroids have had, and in some specific contexts continue to have, their place. It boils down to fitness for purpose.
Okay, break it down for us.
Sure, so if we look at their core purpose, local spheroids are all about regional accuracy. They deliver the tightest possible fit for a specific area, which was ideal for detailed national mapping or very specific engineering projects back in the day. Global spheroids, by contrast, are designed for global consistency, providing that uniform framework needed for worldwide applications like satellite navigation.
Right, local precision versus global uniformity.
Exactly. Then, regarding their center, local spheroids are often not geocentric. Their center isn't necessarily at the Earth's center of mass. They were deliberately offset for that best regional fit, crucial when ground surveys were the only option. Global spheroids, however, are definitively geocentric, aligned with the Earth's true center of mass, making them perfect for satellite-based systems.
Got it. Offset versus centered.
Then they're fit to the geoid. That means sea level surface. A local spheroid aims for the best fit in a limited area, really hugging the local shape. A global spheroid provides the best overall fit globally, but that means it might have some minor local deviations compared to a tailored local model. For examples, we've talked about Everest 1830 and Clark 1866 as prime local examples, and WGS 84 and GRS 80 as key global ones.
And who uses them?
Traditionally, national mapping agencies heavily relied on local spheroids for their detailed, high-precision work within their borders. Today, GPS, satellite systems, and modern GIS overwhelmingly rely on global ones like WGS 84. It's become the global lingua franca for spatial data.
And finally, consistency.
Right. In terms of coordinate consistency, local spheroids provide consistency limited to their specific region. Global spheroids ensure consistency across the entire planet.
Wow, okay. That really clarifies the trade-off. So for you, the listener, what does this all actually mean when you're looking at a map or using location data?
It means if you're trying to integrate data from different sources, maybe you've got an old, incredibly detailed local survey map from your grandfather's attic, and you want to overlay it with a brand new satellite image from Google Earth. Or maybe you're planning a big cross-country pipeline project that spans areas mapped using different historical systems. You absolutely need to know which spheroid each dataset is based on.
Because if you don't,
You're in for some big surprises, misalignments, errors. This isn't just a tiny offset we're talking about. It can be potential shifts of hundreds of meters.
seriously.
Hundreds.
Oh, yeah.
Enough to make your house appear in your neighbor's yard on an old map if you just overlay things without transforming them properly. Or for a bridge support to be built way off-center from its designed location. It's the kind of fundamental detail that can make or break a major project, cause legal nightmares, or even just make your driving directions subtly, frustratingly wrong. You have to compare apples to apples or transform them so they become comparable.
Okay, so we've got the spheroid, the smooth, mathematical, computationally friendly model. Now let's turn to the other half of our Earth modeling duo, the geoid. If the spheroid is our smooth, perfect oval blueprint, the geoid is... Well, you described the Earth as bumpy before. Is the geoid the bumpy one?
In a manner of speaking, yes. It's definitely the more complex, irregular, and you could say more real or physical model. At its core, the geoid is defined as a complex, irregular surface representing mean sea level extended hypothetically under the continents.
Whoa, okay, unpack that. Mean sea level extended under the continents.
Yeah, think about that for a moment. Imagine the Earth was entirely covered by ocean, completely still. No tides, no currents, no wind piling water up. The surface that water would naturally settle into, shaped only by the Earth's varying gravity and rotation, that surface is the geoid. And we imagine it continuing seamlessly under the land masses, too.
So it's like the true level surface of the Earth, defined by gravity.
Exactly. For this reason, it's often considered the true physical figure of the Earth, because it directly reflects the subtle variations in the gravitational field caused by differences in Earth's internal mass distribution.
Like you mentioned before, the lumpy interior.
Precisely. For instance, dense mountain ranges create slightly stronger local gravity, causing the geoid surface to bulge upwards slightly relative to a perfect spheroid. Conversely, less dense regions, like deep ocean trenches, result in slight dips or depressions in the geoid. It's essentially a map of Earth's gravitational landscape at sea level.
Okay, so why is this lumpy potato geoid, as you called it, so important? Why not just stick with the nice, smooth spheroid?
This is where the why truly comes into play. The geoid isn't just irregular, it's intricately defined by gravity itself, which makes it fundamentally different from the purely mathematical spheroid and incredibly useful for certain things.
Like what?
Let's delve into its key features. First, as we've said, it is a physical, not mathematical surface. Unlike the spheroid, you can't describe the geoid with a simple, elegant equation or just a few parameters like A and F. It's an actual measured physical surface. It's derived from painstaking global gravity measurements collected over decades, from satellites like GRACE and GOCE, from airborne gravimeters flying in planes, and from countless ground surveys. It's a data product, constantly being refined.
Okay, so it's measured, not just calculated.
Correct. Second, and this is a critical property, at every single point on its surface, the geoid is perpendicular to the direction of gravity. Meaning, if you held up a plumb line, a string with a weight on the end, which always points toward the local down due to gravity, that plumb line will always be exactly perpendicular at a 90-degree angle to the geoid surface at that specific point. This makes it what physicists call an equipotential surface. It means the gravitational potential energy is exactly the same everywhere on its surface. Imagine a perfectly smooth ball placed anywhere on the geoid. It wouldn't naturally start rolling in any direction due to gravity alone. It's a level surface in the truest physical sense of the word.
Okay, that's a cool concept. So why is that useful?
That property makes the geoid incredibly important. It serves as the fundamental reference for orthometric heights.
Orthometric heights? What are those?
Orthometric heights, usually denoted with a capital H, are the heights we typically understand and use in daily life. They are measured from the geoid, essentially from that idealized mean sea level.
So when we say Mount Everest is 8,848 meters above sea level.
You're talking about its orthometric height measured from the geoid.
Exactly. It's the real-world height relevant to how water flows, how structures need to be leveled against gravity, and how elevations relate to the true downhill direction.
Okay, so it's crucial for real-world stuff.
Absolutely crucial for practical applications, especially in civil engineering and hydrology. When you're designing a long canal, planning a city's storm drainage system, or building a bridge across a wide valley, you need to know how water will flow and where true level is. And that flow is determined by gravity, which the geoid represents.
Right, water flows downhill according to gravity, not according to some smooth mathematical shape. Precisely. Using the geoid as your height reference ensures that your designs accurately account for the Earth's subtle gravitational variations. It ensures water actually flows downhill in your canal, that bridge decks meet correctly, that building foundations are truly level. Without the geoid, you could literally design a canal where water appears to flow uphill according to your plans, or build a house where the floors aren't actually level.
Yikes. Okay. So, if the spheroid is our perfectly smooth oval blueprint, giving us a nice surface for calculating latitude and longitude, the geoid is the actual slightly lumpy and irregular gravitational reality of our planet. It gives us the true vertical reference for heights, the up and down, based on gravity.
That's a perfect summary. Two distinct but equally vital pieces of the puzzle for understanding and measuring our Earth accurately.
Okay, this feels like a really important moment to nail down the relationship. We've got these two concepts, spheroid and geoid. They sound a bit similar, both modeling the Earth, but you're saying they're fundamentally different.
Fundamentally different, yes, but also intimately related.
Right, so let's really clarify the core distinctions. We've talked about the spheroid as the smooth mathematical model and the geoid as the irregular gravity-defined physical surface. Let's do a quick head-to-head comparison, drawing from how our sources lay it out to make sure we've all got it straight.
Sounds good. When we compare them, it's critical to remember their specific roles and why we actually need both. They aren't in competition, they're partners.
Okay, so first up, definition.
Okay, definition. The geoid is that equipotential surface of the Earth's gravity field that best approximates, in a least square sense, means sea level extended globally. It's physical, gravity-based. The spheroid, or ellipsoid, is a purely mathematical surface generated by rotating an ellipse, chosen for computational convenience to approximate the Earth's shape.
Got it. Physical gravity versus mathematical geometry. Next, surface nature.
Surface nature. The geoid is inherently irregular, reflecting those gravitational anomalies. It's our lumpy potato metaphor. The spheroid is perfectly smooth and regular, by definition, our perfect football.
Basis. What are they based on?
Basis. The geoid is based directly on the Earth's gravity field, derived from actual physical measurements. The spheroid is based purely on geometry, defined by those mathematical parameters A and F.
Okay. And crucially, their use.
Use. This is key. The geoid is primarily used as the reference surface for measuring elevation, specifically orthometric heights, those heights above mean sea level that engineers need and we intuitively understand. The spheroid is used primarily for horizontal mapping, latitude and longitude, and as the reference for GPS positioning and calculating ellipsoidal heights, which we'll define shortly.
Right. Geoid for real height, spheroid for map coordinates, and GPS height.
Yeah.
And examples.
Examples. For geoid models, we have things like EGM 96, Earth Gravitational Model 1996, or the more recent EGM 2008, which are complex grids of gravity values. For spheroids, we've discussed historical ones like Everest 1830 and the global standard WGS 84.
Okay, that's a really clear breakdown. So connecting this back to the bigger picture, it's really about understanding their complementary roles, isn't it?
Exactly. They aren't rivals. They work together in a sort of geodetic symphony. The spheroid gives us that convenient, computationally friendly surface for precisely defining horizontal positions, telling you your latitude and longitude on a map framework.
Right, the where on the smooth map.
And meanwhile, the geoid gives us that vital, gravity-based reference for vertical heights, telling you how high or low something actually is relative to where water would naturally settle, relative to true level.
The true up or down relative to gravity.
Precisely. So spheroid for where on a mathematical plane, geoid for true height based on physics. But this naturally raises an important practical question. How do we bridge the gap between them? especially when it comes to measuring heights accurately for real-world things like construction or figuring out flood zones. How do we get from one to the other?
This sounds like where we need another piece of the puzzle. You mentioned datum earlier. Is this where that comes in?
Exactly. This is where we introduce the concept of a geodetic datum. Think of it as the complete package. It's the framework that actually pins down specific locations on Earth in a universally understood and consistent way within that system.
Okay, so it's more than just the spheroid.
Yes. A geodetic datum is essentially a coordinate system coupled with a specific reference spheroid. It provides the full mathematical model and its orientation and origin relative to the Earth, which is needed to precisely locate geographic positions. It's not just the coordinates themselves, but the entire defined framework that makes those coordinates meaningful. It provides a fixed reference point and orientation for all measurements made within that particular system.
Gotcha. Are there different types of datums?
Yeah, we typically categorize them based on what they primarily define. A horizontal datum is used for mapping surface positions, giving us those familiar latitude and longitude coordinates. This defines where you are horizontally on the map, and it's tied directly to a specific spheroid and how that spheroid is positioned relative to the Earth. A vertical datum, conversely, is used specifically for elevation or heights. This defines how high you are, and it's typically based on or closely related to the geoid, representing that mean sea level reference.
And each datum uses a specific spheroid, you said?
Correct. Each horizontal datum is intrinsically tied to a specific spheroid for its geometric definition. For example, the Everest datum, 1830, which was used historically in India and surrounding regions, explicitly uses the Everest spheroid as its foundational geometric model for horizontal coordinates. It also includes information about where the origin point was and how the spheroid was oriented.
Right.
Similarly, the WGS 84 datum, the global standard for GPS, uses the WGS 84 spheroid as its geometric backbone for horizontal positioning, and importantly, it defines its origin at the Earth's center of mass.
Okay.
Understanding which datum is in use is absolutely critical because it dictates the underlying spheroid, its parameters, its origin, its orientation, and, as we're about to see, how heights are measured and how they relate to the physical reality of the geoid. This is where the distinction between the geoid and spheroid becomes absolutely crucial for practical applications, especially when measuring heights with any kind of engineering level precision. So when we talk about measuring height, we often don't realize there are actually two fundamentally different bases we might be measuring from. This leads to two distinct types of height measurements, and it's where the geoid and spheroid directly interact in a very practical sense.
Okay, two kinds of height. What are they?
First, there's orthometric height, which we usually denote with a capital H. This is the height measured vertically from the geoid from that idealized mean sea level surface that follows gravity.
Right, the one we talked about from Mount Everest.
Exactly. This is the elevation we typically understand and use in daily life, the height of a mountain, the depth of a lake, the elevation marker on a survey benchmark. It's the real-world height that's relevant to processes governed by gravity, like water flow. Engineers and surveyors rely heavily on orthometric heights because they reflect the Earth's true gravitational equipotential surfaces, ensuring things are genuinely level or slope correctly.
Okay, orthometric height equals height above the geoid, means sea level. What's the other one?
The other one is ellipsoidal height, often denoted with a lowercase h. This is the height measured vertically from the reference ellipsoid, that smooth mathematical surface like WGS 84.
Ah, so height above the mathematical model.
Precisely. This is what a GPS receiver often calculates directly. When your car's GPS or your smartphone gives you an elevation reading, it's almost certainly giving you an ellipsoidal height initially. It's positioning you relative to its smooth mathematical model of the Earth.
So it's useful for positioning on that model, but maybe not for knowing actual sea level height.
Exactly. While perfectly useful for determining your 3D position relative to the spheroid, it doesn't directly account for the undulations of the actual gravity field, those lumps and bumps in the geoid. An ellipsoidal height doesn't tell you if water will flow downhill at that location.
Okay, so how do we get from one to the other? How do we connect the GPS height to the real height?
The key to converting between these two height systems, and thus bridging the gap between the mathematical model and the gravitational reality, is a value called the geoid height, or sometimes geoid undulation, usually denoted with a capital N.
Geoid height n, what is that?
N is simply the vertical distance between the ellipsoid and the geoid at any given point on the Earth's surface. It's the crucial vertical offset between the two surfaces.
Okay, so if the ellipsoid is the smooth football and the geoid is the lumpy potato,
Then the geoid height N is the vertical difference, the separation between the surface of the football and the surface of the potato at any specific spot. This value N varies all across the Earth. It can be negative, meaning the geoid is below the ellipsoid, like over some ocean trenches, or positive, meaning the geoid is above the ellipsoid, like over some mountain ranges or dense continental areas. It can vary by tens of meters, even over 100 meters in some places.
wow. And how does n help us convert?
The relationship between these three heights is actually elegantly simple. Orthometric height equals ellipsoidal height h minus geoid height n, so HHN.
HHN, okay.
If you know your ellipsoidal height from GPS, that's h, and you know the geoid height at your location, that's n, which comes from a geoid model like EGM 2008, you can calculate your orthometric height, h, your height above mean sea level.
So let me get this straight. Your GPS gives you h, the height above the smooth math model. But for serious engineering or anything involving water flow or true level, you need h, the height above the lumpy gravity model, the geoid. And bridging that gap requires knowing n, the separation between those two models at your exact location.
You've got it exactly right. Without knowing that geoid height n, you can't reliably translate the mathematical world of GPS ellipsoidal heights into the physical world of gravity, water flow, and orthometric heights. Modern GPS receivers often have geoid models built in, so they can perform this calculation, h n equal h, automatically and display an approximate orthometric height. But the accuracy depends heavily on the quality of the built-in geoid model. For high-precision work, surveyors use very detailed geoid models.
Okay, this is where it all comes together, right? This is where the rubber truly meets the road. All this talk of spheroids, geoids, datums, different kinds of heights, it isn't just, academic theory. It has massive, tangible, practical implications in the real world.
Absolutely. The consequences of not understanding or properly handling these concepts can range from inconvenient errors to potentially dangerous and very expensive mistakes.
And the biggest and most immediate issue you mentioned earlier is datum shift. Tell us more about that. What happens when you mix and match these systems incorrectly?
Right. A datum shift is what happens when you try to combine data or switch between coordinates that are based on different geodetic reference systems, say, moving data from an old map based on a local datum, like Everest 1830, onto a modern system based on a global datum, like WGS 84, without doing it properly.
It's not seamless.
Far from it. It's not a simple one-to-one transition because the underlying spheroids are different shape, size, and centering. The consequences are profound and tangible. You get a horizontal shift in coordinates. The latitude and longitude values for the exact same physical point on the ground will be different in the two systems. And this shift isn't uniform. It varies depending on where you are, but it can easily be up to several hundred meters.
Hundreds of meters. So, my house could appear way down the street on a different map system.
Potentially, yes, if you just took the coordinates from one system and plotted them directly onto a map based on another without transformation. And you also get a vertical shift in heights because the relationship between each spheroid and the geoid is different, meaning the ellipsoidal heights h and potentially the derived orthometric heights h will differ between datums too.
Wow. Okay, let's look at some specific scenarios. Where does this mismatch become really critical?
Well, let's start with surveying and mapping. As we touched on, survey data that was meticulously collected using an older local system, like the Everest 1830 datum, simply cannot be overlaid directly onto modern WGS 84-based maps or satellite imagery without first applying a complex and precise mathematical process called a datum transformation.
Right. Give us that concrete example again.
Okay, take those official topographic map sheets produced by the Survey of India for decades. They predominantly use the Everest 1830 datum, which provided excellent regional accuracy. But your smartphone GPS or a modern survey-grade receiver, it universally uses WGS 84. Now, imagine a civil engineer trying to combine these, maybe planning a new road using the old paper maps for existing features and modern GPS readings for the new alignment. If they just threw those layers together in a geographic information system, GIS, without the proper conversion.
Disaster.
Pretty much. The layers just wouldn't match up correctly. Roads would appear offset from where they actually are. Rivers might look like they cross bridges in the wrong place. Property lines would be completely misrepresented. This leads to significant errors in location, potentially causing construction delays, major cost overruns, legal disputes over land boundaries, or even structurally unsound designs if things are built based on misaligned data.
Okay, that's huge for surveyors and engineers. What about just regular navigation, like using GPS?
For navigation and GPS, the problem is equally real, though often hidden from the casual user by the technology itself. Your everyday GPS device, CarNav, smartphone, handheld hiker GPS, it universally operates using WGS-84 coordinates. Now, if you try to take those WGS-84 coordinates and manually plot them onto an older paper map, or even a poorly prepared digital map based on an older Everest type system, without accounting for the datum shift, you could easily end up with major location errors.
So the map might tell you you're on the road, but you're actually driving through a field.
Exactly that kind of scenario. You could navigate to completely the wrong spot, potentially dangerously so, in unfamiliar terrain or marine environments. This is why many professional navigation systems and even sophisticated consumer apps have built-in datum transformation capabilities. They often work in the background, converting between WGS-84 and various local datums so that the GPS position displayed on the map actually matches the map features correctly. But you need to make sure the map itself is correctly referenced, or that the software knows which datum the map uses.
Okay, and remote sensing, satellite pictures.
In remote sensing and GIS, these considerations are absolutely paramount for data integration. Satellite imagery, which gives us those amazing views of Earth and forms the basis for everything from environmental monitoring to urban planning, is inherently acquired and processed using global spheroids like WGS-84 or GRS-80. That's because the satellites orbit relative to the Earth's center of mass, demanding a geocentric system.
Right.
The challenge arises when you try to integrate this global satellite data with various regional datasets. Think about local government data. Precise property parcel boundaries, census tracts, underground utility lines, historical land use records. These might still be stored or referenced in older local datums tied to local spheroids like Everest.
So mixing global satellite views with local ground data.
Exactly. To achieve accurate overlays for analysis or visualization, say, to see exactly which properties fall within a new proposed development zone seen on satellite, or to assess flood risk by overlaying flood models onto parcel data, you must perform coordinate transformation. Without it, your satellite image of a city might not align correctly with the city's official administrative boundaries or its detailed street network derived from local surveys. This leads to incorrect analyses, potentially flawed planning decisions, and inefficient resource allocation. It's all about making sure different data layers talk the same spatial language.
And finally, back to civil engineering and those heights.
Yes, in surveying and civil engineering, the criticality of using the right height system, orthometric heights based on the geoid, is immense, often with direct safety and financial implications. For any project sensitive to elevation, think about building a long canal where water needs to flow consistently downhill over many kilometers, designing a complex airport runway with precise drainage gradients, constructing a multi-story building where every floor must be perfectly level, or even setting flood defenses, geoid-based orthometric heights, are absolutely essential.
You wouldn't just use the raw GPS height.
You absolutely would not rely on raw GPS ellipsoidal heights directly from the spheroid for this kind of critical work. Those H values, remember, don't account for the subtle yet significant variations in gravity that dictate true downhill and true level. Using them without proper conversion to orthometric heights, HEOHN, could lead to disastrous outcomes. Water refusing to flow or even flowing backwards in a canal, misaligned bridge spans that don't meet in the middle, dangerous pooling of water on supposedly sloped surfaces, structural instabilities in large buildings due to differential settlement on foundations that weren't truly level.
And the difference can be big.
The difference between ellipsoidal height H and orthometric height H, which is that geoid height N, can easily be tens of meters, varying across regions. For an engineer, misjudging elevation by even a few centimeters can be critical. Misjudging by meters due to confusing height systems could lead to catastrophic failure. Precision here is paramount.
Okay, wow. So boiling it all down then, what's the big takeaway for our listeners?
It means that in geodesy and Earth measurement, both the geoid and the spheroid serve complementary, absolutely vital roles. They aren't interchangeable. The geoid gives us that natural gravity-based reference surface, the true representation of level and downhill, essential for understanding heights relative to mean sea level, and for engineering applications involving gravity.
Right, the physical reality.
While the spheroid provides our mathematically convenient, smooth approximation, essential for computing coordinates like latitude and longitude, defining horizontal datums, and providing the geometric basis for satellite systems like GPS.
The mathematical framework.
Exactly. In the specific context we mentioned, like India, the Everest spheroid was historically essential for regional surveying, a truly groundbreaking achievement for its time that allowed the precise mapping of an entire subcontinent based on ground measurements. However, today, WGS-84 is the indispensable global standard, forming the backbone of modern navigation, satellite technologies, and global data sharing. Understanding these differences, the critical need for transformations between systems, and the fundamental relevance of these reference surfaces, spheroid for horizontal, geoid for vertical, is truly crucial for anyone involved with spatial data.
So from students learning GIS to professional surveyors marking property lines to engineers designing infrastructure, even just to everyday GPS users trying to understand their location accurately.
Yes, understanding this helps avoid costly, significant, and potentially dangerous errors in geolocation, mapping, and engineering design. It's about knowing which map you're using and making sure it aligns with the real world in the way you need it to.
Okay, let's bring this down to earth in one more really practical way. How do these abstract models, spheroids, local versus global, impact something as fundamental as measuring distance, like turning degrees on a map into actual kilometers or miles on the ground?
Ah, yes, converting angular distance to linear distance. That's a very common task in geodesy and cartography, and it ties directly back to the reference spheroid you're using.
So we often talk about distances on Earth in terms of degrees of latitude or longitude, right? Like the angular separation between these two cities is 5 degrees.
Exactly. That angular distance is essentially the angle between the 2 points as measured from the center of the Earth, or the center of the reference spheroid.
But that's not very useful for knowing how far you actually have to travel, is it? We need that in meters or kilometers.
Precisely. To make that angular measurement useful in the real world for planning a flight path, calculating the length of a proposed road, or just knowing how far apart things truly are, we need to convert it into a linear distance along the curve of the Earth's surface.
And how does that work? How does the spheroid fit in?
Well, the conversion fundamentally depends on the radius of the reference sphere, or more accurately, the specific geometry of the ellipsoid, our spheroid, being used to approximate the Earth at that location. If you assume the Earth is a perfect sphere, the calculation is simpler but less accurate. If you use a specific spheroid, the calculation accounts for its shape, including that equatorial bulge and polar flattening.
So different spheroids might give slightly different distances for the same angle?
Potentially, yes, especially for very precise work or over long distances, because their radii and curvature are slightly different. The theoretical framework is based on simple arc length geometry. You might remember this from school. Arc length, s equals the angle multiplied by the radius, r. So linear distance, s equals sr.
Yeah, seems simple enough.
It is, but there's a crucial detail. For that formula to work directly, the angle must be expressed in radians, not degrees.
Oh, radians. Okay, How do we handle that since angles are usually given in degrees?
We just need to convert. Since angular distances on maps or from coordinates are predominantly given in degrees, minutes, and seconds, they must be converted to radians first before applying that arc length formula. The conversion factor is straightforward. 1 radian is equal to 180 degrees, so 1 degree is 180 radians. Therefore, E in radians equals in degrees x 180.
Okay, so multiply degrees by pi over 180.
Right. Once you have your angular distance in radians, you can plug it into the arc length formula. So the practical working formula becomes linear distance s if 4c in degrees x 180 sr. This allows us to take a readily available angular measurement, like 1 degree of latitude difference, and convert it into a tangible real-world distance on the ground, but only if we use the correct radius r value from our chosen spheroid for the location we're interested in.
Let's try an example. Put some numbers on this.
Okay, let's take a classic example. Suppose the angular distance between 2 points along the Earth's equator is exactly 1 degree.
Okay, 1 degree of longitude difference right on the equator.
Exactly. Now for r, let's use a common approximation for the Earth's mean radius, which is about 6,371 kilometers.
So plug that into the formula.
Yep. S 1 degree, 180 is 371 kilometers, if you calculate that out. Pi divided by 180 times 6,371.
Oh.
You get approximately 111.19 kilometers.
About 111 kilometers. That sounds familiar. Isn't that the rule of thumb people use? Like 1 degree is about 111 kilometers.
It is. This calculation yields that widely used geodetic rule of thumb. 1 degrees of latitude or longitude is approximately 111 kilometers, especially near the equator. It's a handy mental shortcut for rough estimates.
Like, I sense a but coming. We know the Earth isn't a perfect sphere with a single mean radius.
Exactly. That rule of thumb has its nuances and limitations, especially as you move away from the equator or when high precision is required. And this is precisely where the Earth's ablateness, that squash shape, and our refined geodetic models, the spheroids, really show their importance in this calculation.
Okay, how does ablateness affect it?
Well, it affects latitude and longitude differently. For 1 degrees of latitude, moving north or south, the linear distance remains relatively constant, staying close to that 111.1 kilometer value. This is because lines of latitude are essentially parallel circles that are more or less evenly spaced from the equator to the poles.
Okay, so a degree north-south is always roughly the same distance?
Roughly, yes. There's a slight variation because the Earth isn't perfectly elliptical, but it's relatively small. However, for 1 degrees of longitude, moving east or west, the linear distance varies significantly depending on your latitude.
Right, because lines of longitude squeeze together at the poles.
Precisely. It's about 111.3 kilometers for 1 degree's longitude right at the equator, where the lines are furthest apart. But as you move towards the poles, that distance steadily decreases, shrinking to virtually zero right at the poles, where all the lines of longitude converge at a single point.
So a degree of east-west distance near the Arctic Circle is way shorter than a degree near the equator.
Much, much shorter. This varying distance is a fundamental aspect of working with geographic coordinates and has major implications for things like calculating areas accurately or creating map projections that try to flatten this curved, converging grid onto a flat map.
Okay, and how do the different spheroids play into this distance calculation? Does using Everest versus WGS 84 change the answer?
Yes. For high precision work, it absolutely does. When converting angular distances to linear distances using a specific local spheroid, like Everest 1830, the reference radius r you'd use in the calculation, or more accurately, the radius of curvature at that specific point on the ellipsoid, will differ slightly from what you'd get using a global spheroid like WGS 84.
Because their shapes are slightly different.
Exactly. The Everest spheroid, with its specific semi-major axis of 6,377.276 kilometers and its unique flattening, was optimized for the Indian subcontinent. As our sources note, it consequently yields slightly smaller arc length per degree than WGS 84 in that region, because its shape is subtly different from the best global average shape defined by WGS 84.
Okay, so the difference might be small, but when does it really matter?
The crucial implication here is that for precise geodetic applications, think about cadastral surveys, the ones that legally define property boundaries down to centimeters, or creating highly accurate map projections for engineering or large-scale infrastructure projects. Any linear distance calculations based on angular input must specify the exact reference spheroid being used and account for its precise geometric parameters to achieve the required high accuracy.
So you can't just use the 111-kilometer rule of thumb for that stuff.
Absolutely not. Relying on a generalized radius or using the wrong spheroid's parameters can introduce errors that might seem small per degree but accumulate significantly over large distances, or become critical when dealing with high-precision tasks like property lines or aligning tunnels. It's the difference between a rough estimate good enough for general navigation and a legally binding engineering grade measurement.
So, bottom line, while that 111-kilometer rule of thumb is great for casual purposes for anything high precision, you absolutely need to know which spheroid you're working with, use its specific unique parameters, and make sure everything aligns with the chosen datum, whether that's a local one like Everest for historical data or a global one like WGS 84 for modern applications.
You've nailed it. It really highlights how these seemingly abstract mathematical models form the bedrock of accurate measurement and positioning in our physical world. The details matter. Hashtag tag tag outro.
So where does that leave us? What does this all mean for you, our engaged listener, trying to make sense of your place on this planet?
We've journeyed quite a way, haven't we? From the simple, everyday idea of a round Earth, all the way to the sophisticated, distinct models of the oblate spheroid, that smooth mathematical approximation, and the irregular gravity-defined geoid, which represents the true physical level surface of our planet.
It's quite a conceptual leap.
It is.
And you now know that these aren't just abstract concepts tucked away in geodesy textbooks. They are the fundamental, though often invisible, pieces that underpin everything from the map on your phone plotting your route to the planning of massive civil engineering projects like bridges and tunnels, to how your GPS receiver figures out not just where you are, but maybe even your approximate height above sea level.
And knowledge like this is most valuable when it's understood and applied correctly. We've seen concrete examples of how ignoring these critical distinctions between different datums, between spheroids and geoids, between ellipsoidal and orthometric heights, can lead to location errors, not of inches, but potentially hundreds of meters.
Yeah, those examples were eye-opening.
And we've seen how absolutely essential understanding this framework is for fields like surveying, GIS, remote sensing, modern navigation, and engineering. Of course, there's always more to learn, different perspectives and rich understanding, which just reminds us that critical thinking is so essential in this world, overflowing with information, especially when dealing with data that shapes our perception of the world and the precision we increasingly demand from our technologies.
That's a great point. So here's a final provocative thought for you to mull over. The next time you open a mapping app, check the weather forecast showing global patterns, or even just watch a ship seemingly disappear over the horizon. Take a second to consider that invisible dance of gravity, rotation, and mathematics happening constantly behind the scenes, shaping the very information you're consuming.
The hidden geometry.
Exactly. As we push the boundaries of precision ever further, think about autonomous vehicles needing centimeter-level accuracy, or global climate monitoring trying to measure sea level rise in millimeters, or even planning missions to other planets. How might a deeper, more widespread understanding of these complex Earth models change the way we interact with and demand accuracy from our increasingly data-driven world? What new possibilities open up when we truly grasp the shape of things?
It's a fascinating question for the future.
It really is. Remember, the Earth isn't just a simple sphere. It's a wonderfully complex, dynamic shape that we're constantly striving to understand and model better, one deep dive at a time.